So today we're going to work with right triangle trigonometry, and we're going to start with something kind of fun that comes from a movie that maybe you're familiar with, Star Wars. So let's listen to Han Solo as he's talking to Obi-Wan Kenobi, trying to convince him that he's the guy for the job.
You've never heard of the Millennium Falcon?
Should I have?
It's a ship that made the Kessel run in less than 12 parsecs. I've outrun Imperial.
All right, that line actually bothered me for years. Made the Kessel run in less than 12 parsecs. Now, does anyone know what a parsec is? No. Parsec is a word that comes from the contraction of parallax and second. Now, to give you an idea of what parallax is all about, then here's what I want you to do. I want you to take your finger and put it about 1 foot in front of your nose, and then alternately close the right eye, then the left eye. Now, when you do that, what happens to the background scenery, the stuff behind your finger? Anyone?
It moves left and right.
It shifts, right? It shifts left and right. So it appears to move, even though you know that a lot of things in your line of sight, like the wall and the chair, aren't moving. Now, move your finger all the way to arm's length away and repeat that process. Now what do you see? You still see some shifting, right? But, you know, probably not as much, right?
Right.
Now, that shifting is called the parallax. And what's happening is that, you know, the objects in your line of sight aren't moving. It's just where you're viewing things from is shifting. Now, when ancient astronomers looked out at the night sky, they didn't see any parallax in the stars at all. So one of two things is possible. Either they were fixed, they were never moving, they were just stuck there, or they were unimaginably far away. Of course, we know today that's the latter. But let's get back to what we started with, which is a parsec. A parsec can be thought of this way. If you're some distant star and viewing, say, the sun, and then a little ways from that is going to be the Earth. Now, the distance is sometimes abbreviated as 1 AU, 1 astronomical unit. But since we're one of only 2 countries in the world that uses the English or imperial system, let's regard that as being about 93 million miles on average. It's actually an elliptical shape, but we'll ignore that. Now, this angle is really, really small. So let me test you a little bit. What angle is that? What's its measure? Anyone? What's that notation there? It's not inch, although it does look like that, and in certain contexts it could be that. But when you're talking about an angle, what is it?
Is it second?
Yes, it's 1 second of arc. So remember, 1 degree has 60 minutes, and 1 minute has 60 seconds. So if you work with these two together, you'll find out that 1 second is 1 over 60 squared, or 1 over 3,600ths of a degree. It's a really, really slender angle. But we're going to view the system at that slender angle from a really, really far distance. And let's find out how far away that distance is. So that distance is going to be right here. Let's see. We'll call this X. And we know what this is. So we know 3 pieces of information, actually, we know 2 pieces of information here, kind of a third really. But what we're interested in is figuring out this side. So can you think of a trigonometric function that involves an angle, an opposite side, and an adjacent side? Obviously not the hypotenuse, right? Because the hypotenuse would be over here. That's the longest side.
Tangent?
Tangent. So the tangent of 1 second is going to be opposite over adjacent. So it's going to be 93 million over x. And you can cross multiply, or you can multiply both sides by x to get x tan of 1 second equals 93 million. Or x equals 93 million divided by the tangent of 1 second. And that's the length of a parsec. So let's figure that out. Now there is one thing we have to be careful about. We certainly don't want to use radian mode here, right? That would be kind of a pain. So what else can we do? Probably the easiest solution is to think of that as 1/3600th of a degree. So that's what I'll put in. Yeah, I'm just going to do it here. So we'll do 93 million divided by the tangent. Oh, wait, yeah. I am in degree mode. So that's important there. Divided by the tangent of 1 divided by 3,600. And I should get a really big number. 1.918 times 10 to the 13th. So 1.918 times 10 to the 13th, and that's in miles. Remember, this is in scientific notation. That's what that E13 stuff represented here. So if I wanted to put that in regular decimal notation, I got to move the decimal total of 13 places to the right. So a 1 and then a 9, 180, and then 9 more zeros. Wow, that's a pretty big chunk of change. If you're going to travel that far, pack a good lunch. So we got millions, billions, trillions, 19 trillion miles. Wow, it's a long ways. So that is a parsec. Okay. Now the big thing you should get out of this is a little reminder about seconds and minutes and stuff like that. But more importantly, it's how to work with right triangles. Now in a right triangle, you're always going to have an opposite side, an adjacent side, and a hypotenuse. Hypotenuse obviously has to be across from your right angle, but your opposite and adjacent sides are going to depend where you're viewing from. One other thing, and I'll illustrate this in kind of a dramatic way. Opposite, adjacent, and hypotenuse only apply to right triangles. And to demonstrate that as advertised, let me look at something which is about as far away from a right triangle as possible. Does anyone know what kind of a triangle this is called?
An equilateral.
Wow, well done. Equilateral, basically equal sides, right? So all these sides are the same. And if this was your angle, call it alpha. Clearly you can figure out what the opposite side is, but what's the hypotenuse and what's the adjacent side? They don't exist. It's just not, they're not defined unless you're working with a right triangle. So if you're working with a right triangle, hey, everything's good. Okay. When it does come to working with these triangles, you're going to have two things that are known and one that's unknown. Just pick either sine, cosine, or tangent, whatever is convenient. One of these is going to involve all three parts of your known and unknown information, and then just use that to finish calculating the angle or the side. Cool. All right. Anyone else got a comment or thought on this first one? Good with that first one? Let's go to another one. And I think I've got these downloaded to D2L, although I can put them in the chat if someone needs me to. Well, let's look at another one. And again, what's nice about these things is that they're really applied problems. So let me skate all the way up to the top. So some random problem that I pulled off of my math lab. You've got a skier who gets off the top of this chairlift at Aspen Highlands and then hikes up 660 vertical feet on a trek that covers 3,432 feet. So let's draw a triangle that reflects this. So here and here. Now the author of this problem was really careful to note that the vertical was 660 feet and the horizontal was what, 3432? Yep, 3432. But we want to know what the angle is. How steep is that hike? So, okay, not a problem. This is a right angle. Taking a look at these sides, what would you give their names in terms of opposite, adjacent, and hypotenuse? What's the 660?
Opposite.
Thank you. Opposite. And someone else for this side, what would that be?
Adjacent.
Adjacent. Excellent. So is there a function, a trig function that involves the opposite, adjacent, and an angle?
Tangent.
Yeah, the tangent. So the tangent of theta is going to be 660 over 3432. Now I'll point out right away, well, let's see, I'll finish solving this and then we'll go back. We want to figure out what theta is. Can anyone figure a way to get theta by itself?
Inverse tangent.
Oh, well done. Christina, was that you?
Yeah.
Mirror. All right. Well done. Thank you. Yeah, so if we take the inverse tangent on both sides, then on the left-hand side, these two things cancel each other out. So you're just left with theta equals the inverse tangent of 660 over 3432. Now, it's probably time that I open up my calculator. And the unfortunate thing is that the app seems to take a while to open up. My apologies. I should have that up and running ahead of time. Come on, wake up. All right, guess we're doing it old school. So I've got my calculator in degrees because I'll probably relate to this angle more in degrees than I would in radians. But you know, you're gonna have to do what the problem asks of you. All right, I guess we got this up here, so let me do it here. Let's put your calculator in degree modes, or at least this one in degree mode first. I mean, calculus uses radians because it's absolutely most convenient. It's the right thing to do, but it's not easy to relate to things other than a few special angles there. So let's see. Got degrees, tangent inverse of 660 divided by 3432. So, okay. So about 11 degree angle, which is pretty steep when you're hiking in your ski boots, carrying your skis at an elevation of around 11,500 feet. So, in any case, that's our angle. 10.89, we'll call it. How are we looking on that one? Doing okay with this one? I want to point out something that's different and that bothered me for a while. So a friend made an innocent remark and I put it together. And that is, there's a difference between degrees and percent grade. Now your percent grade is just really the slope. So it's this number. It's 660 divided by 3432. So 660 divided by 3432, let's see what that is. So it's about 19.2 or 0.192 or 19.2%. So as a percentage of the horizontal distance, I traveled quite a vertical distance here. And the slope of that line is about 0.192. So your percent grade and the degrees are just different numbers. In fact, when you're skiing down that slope, you can actually ski down something which is 100% grade. So 100% grade means if you ski, say, 660 feet horizontally, you get 660 feet of vertical as well. So that ratio would be 1. If you're trying to find the angle, it'd be the inverse tangent of 1. That's a 45-degree angle. Okay, enough of that. Let's do a couple other problems, a little bit more like your homework. And we'll do this one, which I called example B, but I threw in another one, so this is really now example C. Okay, and they actually specified theta for us, so let me copy down this triangle. And this one comes right out of my math lab, as did the last one. Maybe. Theta. So B is 5 and A is 11. A very typical thing to do in these types of problems is to ask you to solve the triangle and basically get all the trigonometric values that you can out of this. So it says find the value of each of the 6 trigonometric functions of the angle theta in this figure. So we're going to start by figuring out what the length of this side is. How am I going to do that? How can I figure out what this side is? Anyone? Yeah, Pythagorean Theorem. 5 squared plus 11 squared equals c squared. So that's going to be 146 equals c squared. So c is going to be the square root of 146, which isn't particularly a nice number. Sorry. But with that, we can figure out anything we need. So let me list it this way: sine of theta, cosine of theta, tangent of theta. From what I've seen of my math lab, it will accept things that aren't rationalized. So for instance, the sine of theta is going to be the opposite over the hypotenuse. So it's going to be 5 over the square root of 146. Now, if I actually saw the answer in an answer key, they would rationalize this by multiplying by root 146 over root 146. That'll make the denominator 146. So we'll get 5 square roots of 146 over 146. What's the reciprocal of the sine?
Cosecant.
Cosecant. Thank you. Now, my little trick that I share with my students is this. When you're finding these reciprocal functions, don't take the reciprocal here, take the reciprocal before you rationalize. It's just easier. It's square root of 146 over 5. And you're done. Okay. How about the cosine? From this perspective, what's the cosine going to be?
Adjacent.
11 over
5 over 11.
Yeah, 11 over the square root of 146. Let's take the reciprocal now. The reciprocal of the cosine is which trig function?
Secant.
Secant. So that'd be the square root of 146 over 11. Awesome. Now you can rationalize that. It's just going to be 11 square roots of 146 over 146. Not a particularly nice number, but the tangent is a little bit more friendly. So someone else, someone new today. What's the tangent?
Five over 11.
One, oh, my bad. You go.
All right, somebody said 5 over 11. Perfect, 5 over 11. And there was another voice that was also trying to answer. Why don't you maybe do the cotangent?
The cotangent would be 11 over 5.
Awesome, thank you both. Thank you both. And that's it, awesome. We proved it. So comments or thoughts on that one? That's a bread and butter type problem that, you know, if you saw that on an exam, you'd be like, woohoo, yeah, cool. That one should be pretty straightforward for you. But if there's something that maybe I went over too fast, let me know. Okay there. Let's see. Let's go down to this one. And let me just draw this one for you just to get it set up. So suppose you were headed towards plateau 50 meters high. If the angle of elevation to the top of the plateau is 25 degrees, how far are you from the base of the plateau? So mostly I just want to help you visualize this so you can get the setup correct. So idealized, I'm thinking of a plateau that looks like this. And wherever it is, you know, from where you're standing, this is 50 meters. 50 meters. Now the angle of elevation would be the angle above the ground that your line of sight makes with the ground. So that is 25 degrees. The question is, what's the length of that side? How far are you from the base of that plateau? So you can call that X, you can call it A, J, P, whatever you want, but we need to find X. So we need an angle, or excuse me, we need a trigonometric function that involves this angle and these two sides. What would that be?
Tangent.
Tangent. Tangent of 25 degrees would be 50 over X, opposite over adjacent. Or if you solve for X, that's going to be 50 over tangent of 25. The only thing you have to take care of in calculating that is that your calculator is actually in degree mode. So if it is, great. If not, put it in degree mode, and then we'll calculate that. So I want 50 divided by tangent, there's tangent of 25. Beautiful, so 107.2 meters. Nice. There's one last little thing that I want to cover in this section. Are we okay with these triangle examples so far?
Yes.
Thank you. Let me sketch another triangle, and we'll make sure that this is a right triangle. What can you tell me about the sum of the angles in a triangle? What do you know about the sum of the interior angles of a triangle?
Supposed to equal 180?
Supposed to equal 180. Yep, and it does.
Total, I mean.
Total, yep, it does. Now, by drawing a little box here, what am I saying about this angle?
90 degree.
It's 90 degrees, right? So that's 90 degrees. That means these other two also have to total up to 90 degrees, because 90 and 90 would be the 180. Now, if I call this theta and I call this alpha, let's understand the relationship between theta and alpha. We know that these three angles, 90 plus theta plus alpha, have to be 180. If I subtract 90 from both sides, I get theta plus alpha. Has to be 90. So subtracting 90 from both sides. Or theta is 90 minus alpha, and alpha is 90 minus theta. Either way. So these angles are what are called complementary. They add up to 90 degrees. And the interesting thing is that you get some nice relationships between our angles. So maybe instead of calling this alpha, I can call it 90 minus theta, because that's really what it is. It's kind of like the leftovers. Now, here's the fun thing. These are called cofunction identities. And that is, if I take a look at the sine of theta is going to be the y coordinate divided by the z coordinate, y over opposite over hypotenuse. So y over z. But if I'm looking at this angle, this would be the adjacent side, and that would be the hypotenuse. Which trig function involves the adjacent and the hypotenuse?
Cosine.
Cosine. So that'd be the cosine of this, 90 minus theta. So in other words, it doesn't matter if you take, say, for instance, the sine of 25 or the cosine of 90 minus 25. Those should be the same thing. Let's see that. Now, of course, I'm thinking in degrees here. Let's just see numerically that that's true. So sine of 25 and the cosine of 65. Same thing. Nice. And so you have all kinds of these cofunction identities. Cosine of theta is going to be sine of 90 minus theta. What else? Tangent of theta is going to be the cotangent of 90 minus theta. Cotangent of theta. Can anyone guess? What's the cotangent of theta going to be equal to?
Tangent.
Yep, tangent of 90 minus theta. And then finally, secant of theta. Which function haven't we used here yet? The cosecant. Cosecant of 90 minus theta. And the cosecant of theta equals the secant of 90 minus theta. What you need to get sensitive to is angle pairs that add up to 90 degrees. If they do, you've got a cofunction identity involved. So if you've got yourself a little sheet of identities and or formulas, you might want to add this to the list, just so that you can glance at it. How does this work in terms of our problems? What do they look like? Well, let's take a look at the first one. So tangent of 19 degrees and cosine of 71 degrees. So what's the one thing that might jump out at you? Does anyone see something interesting about those angles? 19 and 71. What jumps out at me is that they add up to 90 degrees. Yeah. So I can rewrite that. Let me copy it down here. So we got the tangent of 19 degrees minus the cotangent of 71 degrees. You could change either one of these, but let's change the cotangent. So the cotangent of theta is going to be the tangent of 90 minus theta. Tangent of 19 degrees minus tangent of 90 minus 71 degrees. Tangent of 19 degrees minus the tangent of 19 degrees. Do I need a calculator to figure this one out?
No.
I'm hoping not. That's just going to be straight up 0. And let's do one more like that. Maybe 2 more like that. We'll work with this one next. Find the exact value of the expression. We've got 1 minus cosine squared of 67 degrees, 67 degrees, minus cosine squared of 23 degrees. Again, you should be seeing that you've got angles that are complementary. This one and this one add up to 90 degrees. I'm going to change one of these. Which one do you want me to change? Doesn't matter. Change to 67, sure. So I'm first of all going to write this as cosine of 67 squared. I mean, this is the same thing, cosine squared of 23, but I'm not going to bother with it like that. Just to kind of get rid of that 2 for the moment so we can concentrate on cleaning this up. This is going to be sine of 90 minus what?
67.
67. And 90 minus 67 is going to be the sine of 23 degrees. And that's still squared.
Which is cosine squared of 23 also from the Pythagorean theorem.
No, well, it does start to look like the Pythagorean theorem. We got sine squared of 23 minus cosine squared of 23. If I factored out the negative from these two, it'd be sine squared of 23 plus cosine squared of 23. Somebody help out Ray here. He's been working hard for me today. What does that equal?
1.
1. Thank you, Christina. 1. So again, I get 1 minus 1, which is 0. Now, I can't really prevent you from using a calculator to check some of these things, but when I grade your assignments, I'd like to see something like this. I'm not going to put like a ton of them on your work, but this is the kind of thing that I'd like to see for the 1 or 2 problems like this you might get. Kind of the last one I'll just talk you through. If you convert sine of 17 degrees to cosine of 73 degrees, so down here, convert that to cosine of 73, and then do likewise with this one, convert that to sine of 73, you'll end up with cosine squared of 73 plus sine squared of 73, and that's equal to 1. All right, that should do it.